everyone, welcome back to our YouTube channel Becoming a ROS Developer. Today we've got Cesare who has just completed the course ROS2 Basics with Python, and he'll be giving us a presentation on that. So first of all, we'll begin by seeing a demonstration of the real robot, and then we'll get into the nitty-gritties about his code base after that. I will now hand over the platform to him so he can begin his presentation. Alright, whenever you're ready.
Thank you. Happy time of the day, wherever you are.
Yep.
We're talking earlier. I'm in morning, somebody's in afternoon, somebody might be watching this and it's evening to you. So what I'm showing here is a ROS jack on the robot on the lab in Barcelona, where you will see the robot turning toward the wall, then aligning with the wall, and then doing a loop around while recording the distance that it traveled and sending us feedback. And I will give more details about it in a few minutes with the presentation, but for now we'll just see it working. It's already compiled the package and sourced it, so now we can launch our main launch file. And you can see that the robot is turning towards the wall, giving us feedback that it's turning, now moving forward. Actually, it was a very short distance.
Yeah.
And now we'll be within 30 centimeters from the wall.
Okay.
So now we'll start moving forward, and we can see the feedback received from the action server.
All right.
Oh, I don't know why it did this. Of course, when you test it, it always works, and then when you
What do you want it?
It stopped.
Yeah.
I tested about 6 times, and I don't know why it stopped now.
Let's see how it behaves in a couple of tries, and maybe we might need to disconnect and connect again.
Yeah, well,
but it's all right.
Yeah, I can tell you why. Like it's the I made the check on the initial position, and I will show you later why. Okay, and now it's doing the alignment again, training again, and let's see if this time it goes the way it should. I might say I changed one number, or it didn't test. Okay.
All right. It's a good thing it's moving.
No, it's
And then it stopped again.
Let me comment the change I made recently, because I think that's the one that is causing the issue of that. Okay.
Did you choose very small velocities for control?
I chose very small velocities for one reason that I will talk about.
All right.
Oh, I forgot the semicolon. And again, of course, I tested it multiple times and it always works. So, of course, now that we're doing this live, it's not working.
Yeah, I think it will work this time around. Let's see. Okay, cool.
So the reason why I chose the short velocities was that I've seen we have a requirement that the robot needs to stop when it's within 5 centimeters from the initial position. And I see that somebody used other different requirements than what they were given. For example, stop after you run 6 meters.
Okay. I think I see what's going on here. Yeah.
Yeah. So right now there is a check that it says if your next stop, like the first point you do, is within those 5 centimeters, don't stop. Do the thing, and then stop only when the final loop is done.
Okay.
But I'm surprised that now it's stopping after the first step, because it actually makes this check that is like, hey, look, you need to keep going, and like it's doing this time. So it's that one number that I changed last minute. I went back to a better version.
I see.
So now it's doing properly.
Yep.
Moving slow within 30 centimeters from the wall, adjusting left and right. For example, now it's going too close to the wall, and now I saw a wall in front, so it does the sharp turn left to keep the turn. Now we'll keep following this corridor. Also, the corridor is narrower. Again, I will explain why. The requirement we've been giving is that the robot keeps between 20 and 30 centimeters from the wall.
All right.
Uh, and this could cause trouble with the requirement of stopping when within 5 centimeters from the starting point,
Mm-hmm.
because it happened that the rover, for example, started 30 centimeters from the wall, and after one lap it was 20 centimeters from the wall, which is also a valid and acceptable distance, but they wouldn't be within 5 centimeters of the initial
Oh,
position,
I see. I see. I
and
see.
that would cause the robot to not stop.
Okay. Okay.
Uh, which can also easily be solved by adding a secondary option, which the robot, for example, I don't have it here, but the robot stops when it's within 5 centimeters of the initial position, or it ran more, for example, than 7 meters or 8 meters.
Okay. So you
Uh,
increase the range.
I didn't do that, but it's something that can be done.
That
What I
can be
did
done.
is I made the corridor narrower,
Okay. Okay. I see. I see. Yeah.
25 and 30 centimeters. Um, so while the robot does the last turns, I just wanted to spend a minute saying something about myself. I'm a little bit of an exception, I think,
Mm-hmm.
among students of the Construct Robotics Institute, because I actually have a master's degree in robotics engineering. I
Okay.
received that in 2007, that is before ROS was even a thing.
Okay. I
And
see.
last 15 years, I've been working on a different field. I've been getting my PhD in systems engineering, and so I completely abandoned robotics. Now that I want to go back to robotics, what I'm doing is UX Institute to learn about ROS, because I wasn't familiar with that. So I'm learning ROS, brushing Python,
Mm-hmm. Mm-hmm.
which of course is really useful.
Yes. Yes.
And so I got this little strange situation of knowing a little bit about robotics but being completely not knowledgeable on ROS. So as we can see, the robot stopped and the action returned as required a list of all the waypoints that the robot um, traveled through.
Yes. Yes.
So besides the current distance, we have a list of geometry points,
Mm-hmm.
uh, which was the requirement.
Okay, that's good, and I'm also glad that it stopped immediately after reaching the initial point. So that's quite good. That's quite good. All right.
Okay, if you have questions
Um,
already, I can. Otherwise, I can go with the presentation.
I think let's go with the presentation. So I
Sounds
see it
good.
looks quite nice. So I'm keen to see
Oh, I thank you.
what's in it. Yep.
Okay, first of all, for people that are unfamiliar with this course, this is a basic ROS2 knowledge and Python version.
Mm-hmm.
And the final goal that what you've seen was writing Python code that allows a Turtlebot 3 to follow the wall using laser scanners to keep within a certain distance from the wall,
Yes.
turning when there's a wall in front of the robot. And this was to practice the concept of topics. Then, before actually doing this following behavior, as you've seen, use laser scanners to identify the nearest wall, moving towards it,
Mm-hmm.
and align with the wall.
Mm-hmm.
And this is a ROS2 service client and server. But we also want to measure the progressive distance travel. You've seen we could read current distance travel
Mm-hmm.
and record these points that we traversed. So this would be a ROS2 action client and server.
Mm-hmm.
And for each of the three parts, these were first tested and debugged in the simulator and then on the real robot in the lab. So for each part, I will write what the requirements were and then the problems I met and how I addressed them.
Mm-hmm.
So the first part, which was just the wall following behavior, and you can see here in the picture the simulation that we used to test it. This is a simple subscriber to a topic that already exists, a topic from interface laser scan. So we can read the laser scans from the robot and know where the walls and the obstacles are.
Mm-hmm.
And then there's a publisher on the topic command velocity to send commands to the wheel. So the requirements were that if the robot is within less than 20 centimeters from the wall, it corrects by moving slightly left.
Mm-hmm.
if it's more than 30 centimeters from the wall, corrects by moving slightly right. And it is seen when the wall is in front of the robot makes a sharp left turn. And otherwise it goes straight. And when we had only the wall following, there was no stopping criteria, so the robot will just keep going around in loops. I met only a couple of problems here. The first was that after debugging in the simulation, the real robot kept turning towards the wall
Yeah,
in
yeah.
the real robot. So what I did was using the commands interface show and topic echo to learn what was the numbering of the laser sensors. And so what I did was initializing the variables that have just a different number of sensors for front and for right. And actually, I added a note for myself here. The best code in practice would have been not to do this in the code changing front and right, but having a initial flag, a variable that just says if we are doing the real robot or the simulation, and then use that.
I see. I see. Okay.
That just my picky note.
Yeah, it's quite nice. Just thinking about it, it makes your code amenable to either using in simulation or on the real robot without really like thinking about it, right? So
Yeah.
yeah, that's quite good.
And then the second problem was that the robot in the beginning, when I was using different velocities, had very abrupt movements, especially when correcting.
Yeah.
It
Yes.
wasn't that didn't seem like a fluid movement. So what I did was testing different linear and angular speeds, angular velocities, and also I used different values for the simulation and for the real robot. And I will explain in a couple slides. While in the end, I chose to do slower velocities. So
All right.
it
All
made
right.
first of all it made the movement smooth,
Yeah.
and then it solved some of our problems with the requirement of stopping within 5 centimeters of the initial distance.
Yeah, it's a very interesting approach actually. That considering that you can actually change the numbers like you did, make them slightly smaller for the real robot. I'll also speak about the other way you could have done it, but yep, let's go on.
Second part, the wall finder, which is a service server that makes the robot identify the nearest wall, turning to face it, moving towards the wall until within 30 centimeters, and then turning to align with the wall on the right side.
Yeah.
And here I started using multi-threading, and I wanted to test both ways to do multi-threading. So in this one, I'm using exclusive callback groups.
Right. Right.
That allows me to read the laser scanner while moving.
Okay, I see.
And even here, a couple of problems. The first is that if I used only one laser to identify while rotating or while moving, if the nearest wall was front, that could cause a wrong behavior because sometimes because of the way the lasers work and oscillate a little bit, the nearest wall might not be the one right in front. So what I did is I use a range of indices, so the robot doesn't stop when it's exactly in front, but within 4 degrees from the desired direction.
Okay.
That was a little simple change, because sometimes when rotating, especially when rotating fast, it wouldn't always have the front laser to give the nearest. Sometimes it was the one that is half degree to the left or
Right.
to the right.
Right. Okay. So there will be that like delay in the update, or it will update with the wrong values because it's rotating pretty fast and the value changes quickly.
Correct.
Yeah.
And the same as for the other thing that you were mentioning earlier, that will also be with the Odom recorder. Another solution here is to just use timer of different speed.
Okay.
So updating the laser reading faster than we are moving.
All right. Yes, that will definitely do the trick. Yeah.
And the second, that was probably my biggest issue in this whole project. I had some difficulty with the call of this server before starting the wall following behavior. So I often met deadlocks when I was using timers, of course, or sometimes even with synchronous call, asynchronous multi-threading. So in the end, the solution I chose among the various that could be done is using an asynchronous call to the client, with a spinning check on the response, and then once the wall is found, so the wall following spinner returned that it was done with the operations, I use this flag of wall found to run all the other operations.
Okay.
So do
Okay.
the wall following only if the wall has been found.
Oh, okay. All right. So you're saying, if I understand you right, you're saying while the wolf finder is still trying to find the wolf, all the other control programs will be trying to run at the same time. So you would end up having a blocking situation, sort of.
Correct. Otherwise, I could have done just synchronous, but I don't know why I was having trouble with the synchronous call.
Yeah.
I should have a goal handle to tell the timer when the goal handle was done to then start the wall following.
Yeah. Oh, maybe.
Again,
Okay.
multiple
I would have
choice.
thought because it was I think one of the complications came from the fact that they are all happening in the same node, right? But I if you an asynchronous call would be good enough, right? Because under the assumption that the service that's supposed to the service client that's supposed to give or to call the service server to let it know that I have found the wall would execute first, right? So that would work under asynchronous program. But I think maybe because everything is in one node, so sometimes it's difficult to keep track of who is happening first before the other.
Yeah, correct. If I don't use this tag, what would happen is that the synchronous call happens, but then there's no response returned yet,
Oh,
and
yeah.
the spinner will go through the functions of the wall following behavior.
Uh huh. Okay. Okay. That says it all. Okay.
Well, again, there were multiple solutions here. This is one. Probably synchronous would be the best. But I had trouble after the end of the synchronous call
Uh huh.
with running the spinner.
Okay.
The
All
spinner
right.
had already started and would not get a handle.
Okay.
Final part. This is an action server that you've seen in action that records the robot odometry while following the wall. So when the action is called by a client, and in our case we call this action after finishing the alignment with the wall, so before starting the wall following behavior,
Mm-hmm.
the action records the position of the robot each second using this geometry messages point interface. Uh, it returns feedback data every second on the distance covered by the robot. And then when the robot position is within 5 centimeters of the initial position,
Mm-hmm.
it returns the result message that contains the list of all the recorded waypoints. So we have a track of where the robot walked. Even here, I use multi-threading. This time I use the other way of doing multi-threading with re-entrant callback groups.
Mm-hmm.
So they the odometry while the server messages are running. So you
Mm-hmm.
have the two threads that are running in the odometry recorder.
Mm-hmm. So
Only
so
one issue here.
okay.
Sorry, go ahead.
On the two types of callback groups you used, what are the main differences between the two? So the other time you mentioned using mutually exclusive ones, and then this time re-entrant callback
Yeah,
groups. Yeah.
yeah, they both allow to run callbacks at the same time. We use the mutually exclusive, usually when they're touching or reading or writing sensors or variables at the same time,
Right. So
because
that
if we enter call groups, we wouldn't know when the variables had been updated,
right.
and
So, okay. I see. So you're saying that you want one of them to give priority to the other when you use mutually exclusive callback groups.
or at least we know what is the sequence, so that we don't
Ah,
decide the priority.
yeah, yeah, yeah. But there's always a certain order of execution, right? Okay. No
Correct.
con. It's not pure concurrency.
Instead, multi-threading with reentrant is concurrent, and that's why they are both in the same group, but it's a reentrant
Ah,
callback group.
okay, okay, all right.
The one issue here that we actually seen in action was the stopping criteria. So as I mentioned already, the initial conditions that the robot needs to follow the wall between 20 and 30 centimeters might cause the robot to be further away than 5 centimeters from the initial position after one lap.
Yes, yes.
And so I reduced the corridor here. Um, and the second was that if I go slow, which I'm doing in my case, the first reading after the initial position which is actually what was happening,
Mm-hmm.
might be still within the 5 centimeters
Yeah, within
because we
the
are stop.
yeah, yeah.
So there are multiple solutions possible here, different timers, different stopping criteria. The solution I chose was keeping the requirement of going back to 5 centimeters.
Mm-hmm.
And so what I did was, first of all, let's lower robot speed
Mm-hmm.
so that we can be more precise and we can be sure that by the time we check, we are not already past. We might do one loop
Okay.
and then we are 10 centimeters from the initial position, and then one step later, we are 20 centimeters past. So we never are
We,
within those 5 centimeters.
right. You never stop. Right. I see.
Uh, but if we use the solution I use of this lower robot speed,
Mm-hmm.
what we need to do at every step, we need to check that the new position is more than 5 centimeters from the previous position so that we avoid that initial lock of, well, you moved only 3 centimeters, so now you're within five
So you
from the
can
initial
stop.
position. I will stop.
Yeah.
And
Yeah.
that's the last check.
Uh-huh. I see. I
That,
see.
and this is it. This is all the problems that I found that I had to debug and solve.
All right. Very interesting. I like the way you put it across. Right. It's quite nice to see the different perspectives of the same solutions. I know of this solutions to the same problem. Right. So um,
Yeah.
that is really good. So thank you very much. It's been a wonderful presentation. So in terms of questions, I've been asking as we go, but let me see. Okay, so this is abstract, but I would like to know what if you had used a faster velocity, right? Um, like we did, right? We used a slightly faster velocity to get it out of that 0 to 5 centimeter zone, right?
Yeah, I
And
think with the faster velocity, the only thing I would need to do is using a faster timer
mm-hmm,
for the callback, which I think is the feedback callback, which is the one that checks the distance
yeah,
from the initial position. So
yeah,
I would move the robot faster. I would update the waypoints still every second,
yeah,
but I would probably put a timer on the feedback callback maybe at 0.1 so
yeah,
that the feedback callback can still read the odometry, even
right.
if that is not recorded, and say, well, we are now within 5 centimeters.
Yeah, yeah. It's so it's almost like a sampling speed kind of scenario, right? Where you'd increase your sampling speed because it's going faster, right? So you want it to be constantly checking as often as
Yeah.
possible because things might change a lot quicker. So yep, that's pretty good. That's pretty good. Okay. Another thing that I would have wanted to ask is, so you did make use of services and actions, right? Can you give me some detailed differences between the two, right? Because they all have
Yeah,
clients, they all have servers, right? But let's speak about
yeah,
their
this is actually
differences.
really simple, and I can. Oh, the the session ended, but I think I can still go look here.
Yep.
Uh, so the simple difference, and I think I have them in custom interfaces. Uh, you can actually see from the file.
Mm-hmm.
Uh, Server requires only two pieces of information. In this case, one is not uh, necessary.
All right.
So we got a request, we got a setup request, and then we got a result that is returned
Mm-hmm.
by the server, by the service server.
Mm-hmm.
For an action, we have three parts.
All right.
We have again a goal request, which in this case is empty. Then we have a final result, but we have a third part, which is at feedback.
All right.
So the
Right.
difference is that once the service is called, the service will run
Mm-hmm.
whatever happened,
Mm-hmm.
or
Mm-hmm.
it will stop if some issue happens. An action gives continuous feedback that can be called by the client or shown in a call from command line,
Right.
and this feedback can be used to actually terminate the action ahead of time if
Okay.
necessary.
Preempt. Yes. Okay.
And so this is the main difference and this is a topic that the action server will publish into.
Mm-hmm. What about um the process in which they execute, right? So are actions blocking? How are they spun in comparison to services, right?
Oh, actions are not blocking because they have to give constant feedback.
Mm-hmm. Okay, what about
So
services
we are
on the other hand? Why do you think services have to block?
well, service had to block because they don't have the feedback. They will have to return a result.
Mm-hmm.
So even we call the service asynchronously, we will have a future that we need
Object
to
that
check.
you suppose, yes, you're supposed to receive before continuing with the execution, right? Right. All right. Very nice presentation again, Cesare. Thank you very much, and congratulations. All right, everyone. So this was Cesare's presentation. Very well explained, and warm congratulations to you. So until next time, we'd like to encourage all those of you who would want to come and showcase their presentations to do so.